Hi everyone. Today I'm joined by Zeqi Xiao, a second-year PhD student at the MMLab at Nanyang Technological University, where he's currently pushing the boundaries of generative models, particularly in video generation as well as world simulation. Zeqi has already previously interned at the Shanghai AI Lab, collaborating with leading researchers on doing generative model work. He holds a bachelor's degree from Zhejiang University and has co-authored a series of impressive papers at top-tier venues like CVPR, ICLR, and NeuralIPS. But today we're diving into his latest work, WorldMEM, a framework for long-term consistent world simulation with memory. It's an ambitious step forward towards generative models that can imagine not only detailed scenes, but also remember previous ones and evolve along time. So, Zhe, welcome to the show. Excited to have you today.
Okay, thank you for the introduction. I'm very happy to be here at the Hack Club. And today, gonna also introduce some of myself. I'm now a PhD in NTU, and my supervisor is Professor Xinggang Pan. And I'm now focusing on generative models, especially for video generation. And I'm particularly interested in video diffusion model or video generative models for word simulation. And I think that would be a very promising and potential direction for further like word simulation or gaming or other stuff. Yeah.
Yeah, sounds awesome. Do you want to maybe go into the beginning of the paper? I know there's a lot of people on Twitter maybe who've seen these like videos of like the future of gaming where it's like all AI generated terrains and a lot of glitchy stuff happening when they're looking at these videos. Like for example, the AI just forgets previous scenes and forgets an object like a forest in Minecraft was previously in this position, but then it disappears when the user swivels their head back. So, do you want to maybe go a little bit more in depth on what the problem is and how WorldMem is like attempting to solve it?
Okay. I will try to make high level ideas and make a simple introduction of that. So
Hmm.
the problem of this area is that there have been a lot of prior works done on word simulation or gaming by video generating models. Like I've seen some work for CS:GO or other games like also Minecraft, but they have the same problem that they just keep generating and they just discard previous contents and forever forget them. So my target is to just make a consistent word. We not discard this information, but build a memory bank to store them. So for next generation, we just retrieve some important information from the memory bank to guide our generation. So hopefully, with the memory including like visual contents and other states like pose or timestamps, and with this information, hopefully we can like memory the content and generate a consistent word. And I've done some experiments on especially the Minecraft word. And so in the future, I think I will extend and scale up this to like real world things. So that would be more fancy and cool, I think. Yeah.
Yeah, that sounds really, really interesting. I want to look a little bit more at maybe how you're doing this retrieval. So I know your paper talks about like an external memory bank, and you use
Yeah.
some sort of embedding to store the spatial representation of previous frames in that memory bank. Could you maybe explain what these embeddings are? I know your paper talks about Plucker embeddings, but I'm just not really sure what that specifically is. So could you maybe explain it a little bit more?
Okay, so there are something about this part. There are how we formulate the memory bank, right? And how we
Hmm.
retrieve this information and how we use this information to guide the generation. There, I can split this into three parts. Like, so for the first part, how we formulate the memory bank. So actually, the memory bank have several memory units, and in each unit, it include one frame visual content and its corresponding states, like I just said, the poses and the state and timestamps. And since actually this work is an initial step toward a consistent word generation, so we just like build this state. So in the future, there will be more states and more information stored in the memory bank for generation.
Hmm.
So for this work, just these things, and for the retrieval algorithm, actually, it's also a very initial step. It's a kind of handcrafted algorithm. So the high level idea is that we calculate a confidence score for each memory unit, and how to calculate the score. And the high level idea is first use the view overlapping of the things in memory units and current generated frame. So if we have higher view overlapping, there will be higher confidence score, because it means that this memory unit have more information that we need for current generation. So another aspect is the time step. So the high level idea is that the closer the time step of memory unit and current generation is, the higher score it will get. So we just manage these things to figure out a confidence score and to retrieve high confidence score memory into our generation to guide this. Yeah.
Yeah, that's really interesting. Do you want to maybe share your screen to show some of the videos that WorldMem was able to generate?
Okay.
And in the meanwhile, for the videos that were generated by WorldMem, were those in real time, like as the user was interacting with the controller or a keyboard?
No, unfortunately, it's not real time now. I also seen
Mhm.
some real time work that's specific work on this aspect, but we just care more about the consistency. So we just choose some baseline method and improve above it. But for the real time, I think it's also an interesting problem, and we will also yeah, look into these problems later.
Yeah,
So.
definitely.
And currently, it's on my GPU, H200 is like 1 second for one frame.
So
And yeah,
for one of the videos on the projects, I guess it probably took like a few hours to generate, right?
uh, you mean the videos? Not so long. It's like a
Hmm.
one frame for 1 second. So to generate a 100 frame video, we just need like more than 1 minutes. And that not
Oh yeah.
so long.
Hmm.
Yeah.
Yeah, I guess like Minecraft isn't that much FPS if you wanted it to be. That makes
Yeah.
sense. So I think I like maybe could you scroll down and let's look a little bit more at the videos because I just really want to highlight to everyone watching how incredible it is at actually like remembering the spatial relations.
Okay. So, how do you plan to introduce it? Or with my logic to introduce this?
Yeah, so I guess could you maybe do like explain a little bit about how the images are generated? To my understanding, you use diffusion, right? Could you maybe
Yeah.
explain what diffusion models are able to do and why they're really good at image generation?
Okay. Then we go to the paper. Can you see my
Hmm.
screen?
Yep, I can see it.
Okay. So I guess that not many people understand how diffusion works, right?
Hmm. Could
So,
you, yeah, a little bit of like a bird's eye view overview if you could.
okay. So, okay. So I can just open some slides. There might be some, yeah, high level structure.
That works.
Okay, we can see these slides for like high level understanding. So
Hmm.
what the diffusion model actually do is that we can input some noisy frames like this, and we just input them into the diffusion model, and the diffusion model will denoise them for several steps, and after that it will output clear frames, looks like this.
Yeah. So I know recent times some applications like GPT-4o might be using more of like a transformer architecture in order to generate these images. Do you maybe know why some people prefer to use diffusion for video and like image generation, while some think that maybe transformers might be a better approach?
Yeah, actually, uh, diffusion model now also use the transformer. So you may want to ask that the difference between like the diffusion or just the next token prediction.
Yeah, so
Yeah, yeah.
what's I guess maybe the difference there is that diffusion is actually quite a lot faster, correct, than next token prediction for each pixel in the image?
Not really. Sometimes next token prediction would be faster, but I think the advantage of diffusion is that because it can diffuse for several step, oh sorry, denoise for several step.
Hmm.
So normally it can get higher quality. So that's the image or video generative model care about. So now it's still the mainstream to use diffusion model to do these tasks.
Yeah, why do you think it is that diffusion models are a lot better at creating more high quality images than next token prediction? Is there something inherent to the way the architecture is done, or is it maybe more of something to do with how these models are trained?
Yeah, that's a good question. So I think for a simple reason is that next prediction, they just predict the final result for one time. But
Hmm.
the diffusion model, it will like formulate the process into multi-step denoising step. So in this way, it will gradually denoise it, and in the final result, it would be better. And now I've also seen some results that combine the advantage of like next prediction and diffusion. So they will not
Hmm.
directly predict the final token, but just predict some result and then use diffusion model to find further denoise it. So that would get better results from some projects I have seen.
That makes a lot of sense, actually. And
Yeah.
to talk a little bit more about how diffusion works, is it similar to like an LLM where it's autoregressive and it feeds itself like the image to continually denoise? Or are there like multiple layers in the model and then it like slowly takes out noise throughout the layers of the model?
Actually, it's typically use one model to diffuse,
Mhm.
but we will feed also the time step. So diffusion model needs a lot of time step, right? So when we input this noisy frame, we also input the corresponding time step. That indicates the noise level of these frames. So we input them into the model and get a little bit better result. And then we again feed this little bit better result into the model again, and then further denoise it and also input the time step. So we just use one model and input the time step to indicate what level it's now, and then gradually refine it.
For the training of these diffusion models, how do you go about like turning these really high quality images in the training set into a bunch of like noisy frames that progressively get more clear as like a training data set? And how does that like entire process look like?
You mean the training process, right? So
Hmm.
the target is just to let the model know that given what kind of noisy level, what should I output next? So it means that the model need to know and learn and see all diffusion levels as input and output something. So in the training, we just like uh, get some videos for the video diffusion model and add different level noise to it, and then feed it into the video diffusion model to denoise it. So in this way, with a lot of data training, the video diffusion model will learn. Oh, I've seen plenty of noise levels, and I know how to deal with these noise levels and output a reasonable result. Yeah.
I guess taking a step before how these images are generated, there's like a text prompt that is given to the model, correct? Like it should
Yeah,
generate a Minecraft scene with this in the background, a tree next to the user, or something like that, correct?
yeah. Text prompt is actually one kind of a control signal we can input, and there are also signals like actions or other things. Everything you want to like have give a signal you can input into the model as a condition for generation. Yeah.
So going a little bit more deeply on this cross attention idea you had in your paper, could you
Uh,
explain how we use that cross attention, right, to influence how the diffusion model gives its output?
Okay, so for this work, we model the we use a memory block and use the cross attention to model the relationship between the memory frame and the current generated frame. So our goal is we need to draw information from these memory frames to influence our current generating frame. So we model them into a cross attention because cross attention has a formulation that we can use query, key, and value to do the process, right? So we can just use the frames that we want to denoise as a query and use the frame bank memory frames as key and value. So in this way, we use this query to query information from the memory frames to draw information to influence the generation. I'm not sure if that's clear enough.
Yeah, I sort of understand what you're talking about, right? There's
Yeah.
similar to like a large language model, there's this attention mechanism. I guess how does this cross attention approach combine with your plucker embeddings? Does the plucker embeddings narrow it first before you then do the attention stuff?
Oh, you mean the Clark embedding?
Uh-huh. How
Yeah,
does
yeah.
that like fit into everything?
Yeah,
Sorry to ask.
yeah. This plugin embedding is generated from the post, right? The view post. So its function is like to help the query and the key process to learn the similarity between or the relationship between current generated frame and memory frame. So with this plugin embedding, we add them respectively into the query and the key. So in the query key process, they will know. Let me just give some example. So if
Hmm.
we have a frame like this view and a memory frame in this view, so they have different plucker embedding. So this current view is query, and this memory is the key. So with this embedding, we can just compute the relation between this query and the key and figure out an attention map uh, to draw information from the memory frame.
So for the plucker embeddings, it's calculating like the field of view and like all the points in space that would be in the field of view. Am I getting that correct?
Sorry, what view?
Yeah, wait, sorry. So what is a plucker embedding? I guess that's like something that's a little foggy to me right now.
Yeah. So plug embedding, you can So we can start from a normal embedding, like we just for each view we have its pose with x, y, z, pitch, and yaw in our
Hmm.
definition. So actually we can just turn this information into a single embedding, right? So we just we use a network to learn embedding for this frame. So that's one way to do that. But why we use plug embedding is that it's a method that is not full can be
Oh, yeah.
forced into a dense representation for each pixels, so that each pixel has its information. So with this dense embedding, we can more detailed compute the relationship between the query and the key.
Do you have a diagram in the slideshow to maybe explain to the audience how this plucker embedding space looks like?
Okay, I know that some paper draw that map, but I actually did not draw that.
Okay, no
I
problem.
show you one paper, also a very good paper.
Everyone check this paper out.
Yeah, it has the map, I think. So this is basically the plug embedding. So we have some parameters denote the view pose. Like here, you can just understand it as the pose and angle. So so normally this is one set of parameter for one frame. So that would be a normal way. But for plug embedding, it will turn one set of parameters into a dense representation. So we see that for each pixel on this frame, it will have a special and different information denote the position of this pixel. So that would be a dense representation and a more detailed representation. But actually, if you want to get the idea of this paper, that is not a key factor. Yeah.
Okay, I see. So, um, maybe talk a little bit about how the attentions are trained. So I know, yep, you have like looking at whether or not the field of view is pointed in the same direction, maybe looking at the timestamp. How is like the actual attention like values trained?
Oh, you mean how this attention is trained?
Hmm.
So actually, it's just go through a normal or trend process, like I just said. We just follow the diffusion training process, and we just add the block to the architecture and use the normal process to train it, and it will learn some parameters, some weights of the model will be optimized for this model to learn how to reason the relationship between the query and the key. And in this way, finally, it can learn, oh, query is on this view and the key is on this view, and I know how to draw information from this view to the query to influence the generation. Yeah.
Sounds like a plan. When you take the previous frames that are like the most highly attending to the current frame, right? How do
Yeah.
you tell the diffusion model to like mimic the things it's seeing in that old frame?
Yeah. I think that's just a learning process. So we just give the right architecture and give the right data and give the right supervision. It will learn that how to yeah, that's magic machine learning, I think.
Yeah, so you just feed it the previous frame and it just like knows what to do and knows how to reconstruct it with minimal loss, basically.
Yeah, yeah.
Okay, makes a lot of sense. I think maybe one thing we should touch a little bit more on are the future applications. I know at the beginning of this presentation, you told us a lot about how you are really interested in world simulation. Could you maybe explain some of the motivation behind why you are doing this field of research?
Yeah, okay. I think this is also in the slides. Uh, no. This slides. So I can enlarge this one.
Mhm.
So this is the above is the basic video diffusion architecture, right? So now we have seen a lot of advancement on this field, which is also very like shock me the progress it make. Like we can see for one direction, now video diffusion models can generate a very high quality results, like this result from 2.1. And we can see that it can generate very high quality car running very realistic cities. And also there are some exploration on the open world simulation on video diffusion models. So we can see that there are examples from the Genie 2 from Google and also Cosmos from NVIDIA. So this work can just accept action or other control signals as input to control the agent, like exploring some realistic or imaginative world. And as I just said, there are like this disadvantage or shortcomings is that their word is typically not consistent. So they will just keep generate and forget the previous things. So consistent would be a very critical problem to solve. But this kind of pattern or paradigm is very promising because imagine in the future, like we can just input a real life image and we can use some keyboard to control ourselves, to explore it, to imagine it, and also interact with the environment, like we can pick up something or destroy something. So I think that would be beyond like a gaming, but more than a new paradigm of exploring or something. Yeah. And
Yeah,
also,
that's a great way to put it.
yeah, and also there are some fast, interesting downstream tasks that we can do with diffusion models. So like uh, because we have very good diffusion models as fundamental model, we can do many tasks like re-angle uh, the camera pose of a video. So here is one paper called Recam Master. So in this work, it can input a video, a random video, and re-angle the camera pose of this video. So it's actually very helpful for filmmaking, I think. So we can just uh, capture some videos and randomly do the camera pose estimation and input some new angle frame videos. Yeah, and just this is just one case. There, I think a plenty of downstream tasks that would be promising.
I know one of the roadblocks you talked about for these types of world simulation models is like the inference time, right? It takes about a second for each frame to be generated. Are there any ideas you see that are really promising right now about how maybe we could get inference to be a lot faster and potentially get into a world in which this might be real time?
Yeah, yeah. I think as time goes by, there will be a lot of work uh, like focus on this field. I've also seen some of this one. I can just show you some examples.
Hmm.
Recent game pro use video generative models and it's actually achieve real time. We can see we can just play this game uh, in real time and input some actions to like control the agent to do something. And this is also I think initial step with it because it also have some problems. So for one problem is it's actually um, overfit, like just mimic the map of one game. I actually does not play this game before, but I think the map is fixed. So every time I will start from a same place and everything's are just the same, I think. So, but it's real time and it's done by generative models. So in the future, I think the diversity and other more interesting characteristic for gaming will be proposed. So in the future, hopefully we can play some real-time game with much diversity and many interesting features to do. Yeah.
Wow, that's really interesting. Is this game fully like the AI is generating frame by frame, or is it the AI generated the map and then you're playing on that map?
It's a pure generated and it will generate frame by frame.
Oh, really? That's
Yeah.
really, really fast then. That's really
Yeah, yeah.
interesting. It might be doing some, I guess maybe some tricks in which it's not really. Do you know if it's like a diffusion model doing this, or if it's like there's some
Uh,
tricks where it's rendering a little bit
Actually,
less?
it's more like a GBT, which is next token prediction. So I think this can be faster because what for one reason it's use don't use diffusion model, which would be slower but high quality. Now it's
Hmm.
just use a low resolution and low quality one, and it actually does not need to do too much generation thing because as I just said, the map is actually learn from a fixed scene. So everything is fixed. So it just need to like generate a very small domain of data of things. So that would
Yeah.
be faster. Yeah. Okay.
So for, yeah, maybe when you scale up the model, next token prediction might not be like that much faster than diffusion.
Yeah, for a larger model, that's need to store more things that maybe not so faster. But as time by with better GPU and better like sampling strategy, I think that would be not too hard to achieve. Yeah.
Yeah, so as we start to wrap up this interview for today, I just wanted to highlight a few more of the papers you had published, specifically about the stuff you're doing in diffusion models, stuff you're doing with video motion control. Do you maybe want to highlight some of like your favorite parts of those papers and maybe some of your most like proud findings from those research that you've done?
Okay. Yeah, I can just share my personal project page. So here are some of main product I do. So So at previous one, I actually do intern at Shanghai Lab and do something more related to embodied AI. Also a very interesting direction now, I think. So, but now I'm more focused on video diffusion and
Mm,
so at the beginning, I've done some simple exploration at video diffusion, like we just explore some features of video diffusion models and use them to interpret and control the motion. And it is accepted by the new RIPS 2024. And also, we explore ways to do fine-grained motion control with proposed trajectory attention. So this also includes some interesting results, like we can do camera motion control on images and on videos, and also for video editing. But the most favorite one is the very recent one, the memory, word memory, and it's the direction I think I can do more things about. So yeah, in the future, I will also focus on these aspects, especially for word simulation, and maybe I can access more resources to scale up this kind of methods and do the things that follow my targets. Yeah.
Yeah, and for this WorldMem stuff, if we're looking at the real scenes that you just had on your screen there, where it was like a scan of a room and then making it more interactive, yeah, those seem like really good real world applications in which you're able to like memorize specific locations in the house and then generate what the rest of the house might look like while still having that intact.
Yeah, yeah. And also now it's not real time. I also encourage you, if you are interested, you can try the code or the demo on the online demo if you want. So for this demo, I actually uh, it will actually take a longer time, like 5 seconds for one frame. But I think it's also have some interesting results. Like I put here, you can directly try this example case and immediately see the result that you don't need to wait for too long time. So like this video, we can also show that we can freely explore the word and consistent word. Yeah.
That's really interesting. Wow. And for the generation of the video, you type in like a sequence of actions I saw like in the data set, or is there some
Yeah,
other way to interact with the model?
yeah. Now the input is just like this kind of words as the input, and we are also put some guide here, and you can also try some like example actions here. So it will turn word this word into this action sequences. Yeah, I think that's all. For the introduction of WORLDMEM. And for more details, you feel free to just reach me and ask me and discuss any questions. Yeah.
All right. Thank you so much for presenting your work today, Zeqi. I would like to have you again sometime in the future, maybe if you do more exploratory work, have some more stuff done with WorldMem, and we'd love to see where this project pans out. Thank you for your
Okay.
time. Have a good evening. See y'all.